Okay, here comes our next triangle segment. And again, I have my right, my obtuse, and my acute triangles. This time we're going to be talking about angle bisectors. So we'll start with our acute. And this is a little bit of a harder fold, but what we need to do is fold this angle in half. If I fold the angle in half, then I can draw this side length, this segment that is the bisector that evenly divides this angle. So if your acute angles are too small, it is difficult to fold. Especially for this last one, the fold is difficult. But it's kind of cool when, of course, you see that there is a point of concurrency. It's just crazy. You know how hard it is to get things to line up. The fact that each of these angle bisectors, when drawn and folded, intersect at this one point of concurrency is just crazy. So each of these angles is bisected and they intersect here at this one point of concurrency. And this point of concurrency is called my incenter. Now the crazy thing about this incenter, and I'm again going to get my perpendicular line segment, is this incenter is going to be equidistant to the sides of the triangle. So if I line up my post-it note and my right angle, I can draw each of the angle, each of the distances to the sides of the angle using my right angle with the post-it note. Each of these pink lines is drawn as a perpendicular line segment, and they are all going to be equidistant from this incenter. So for an acute triangle, it's inside of the triangle. Let's see what happens with the right triangle. We'll fold this angle. Now here, we're folding the angles in half. Before we folded the segments in half, and for the angle bisectors, you have to fold the angles in half. And it can be tricky, especially with the really acute angles. But here I go again. I found my incenter. Check it out. Here's this angle bisector. Here is this angle bisector. And here is this angle bisector. I was a little off here with my last line, but I know for a right triangle, when I have my angle bisectors, they all intersect at a point of concurrency that we call the incenter. And this incenter is going to be equidistant from the sides of the angle as measured with a perpendicular line segment. So I know that the distance from the incenter to the opposite side of the angle that was bisected is going to be the same. We had this theorem, so we're not surprised when each of these distance measurements is the same. The tricky part is to make sure you know the difference between the line that is the angle bisector and the perpendicular line. So our right triangle and our acute triangle were both inside of the triangle. Curious about our obtuse triangle. So we'll go ahead and bisect my obtuse triangle angles. That one was an easy fold because it was fat. So for each of these, we're going to fold the angle in half. Each of these, we're going to fold the angle in half. And once again, we're not surprised to see there's our point of concurrency, where each of these segments that bisects the angle, they all meet at one intersection point. Now, you might not think that that's amazing, but it really is. And imagine the mathematician that figured this out. Each of these angle bisectors intersects at one common point of concurrency that we call the in-center. And again, if I measured how far that in-center was from the sides of the triangle with a perpendicular line, I would not be surprised to find out that each of these distances from the in-center to the side of the triangle is the same. Each of these distances is the same. So interesting, our in-centers, no matter what triangle we have, acute, right, or obtuse, all meet inside. The in-center meets inside and is the same distance from each of the sides of the triangle.